At walking speed, a giant transformer moves along a road under escort. A computing campus represents a different speed. Yet, even a ready project may wait for a qualified electrical connection. Without required transformer equipment, it cannot energize on schedule. On April 20th, 2026, the White House issued a Defense Production Act determination covering transformers, conductors, substations, breakers, electronics, relays, capacitor banks, electrical core steel, and manufacturing tools. The administration cited limited domestic production, long procurement timelines, foreign dependence, and insufficient capital as national defense concerns. Digital investment can move in months. Qualified industrial throughput expands in years. That was not a ribbon cutting. The determination said later energy action could include purchases, purchase commitments, and financial instruments, but it named no award, completed factory, or delivered transformer. The machine is a test of whether policy could change the capital signal faster than industry can change qualified throughput. The mechanism is a ladder of voltages. Electricity moves across the bulk system at high voltage, enters substations, and is stepped down through different equipment before reaching a dense computing campus. A transformer changes electrical conditions. It is not the generator, transmission line, breaker, or control system. A data center does not order one magic AI transformer. It needs a coordinated connection of generation, transmission, substations, protection, conductors, transformers, and local distribution. At the final stages, distribution equipment feeds the lower voltage network. At the high voltage end, a large power transformer is part of the substation or generator connection to the wider grid. Between them are other grid components with different ratings and site specifications. If one link is late, the campus connection is late, even when servers, buildings, and generation are ready. The bottleneck is a system schedule, not a single purchase order. Start with the class easiest to confuse. Under DOE's definition, a distribution transformer takes input at no more than 34.5 kilovolts and delivers no more than 600 volts. Liquid units span 10 to 2,500 kilovolt amperes, and dry units 15 to 2,500. A large power transformer is different. DOE describes it as custom equipment with a chain of pre-qualification: bidding, design, manufacture, testing, special transport, delivery, and installation. These classes do not share one countdown. A lead time figure is meaningful only when its transformer class is named. That is why one lead time misleads. DOE reports distribution lead times rising from 3 to 6 months in 2019 to 12 to 30 months in 2023. A 2026 webinar reports distribution demand up 41% since 2019 and lead times of 1 to 2 years or longer in 2024. The same webinar says large substation and generator transformers can take 3 to 4 years. DOE's Large Power Report records producer discussions of manufacturing and delivery times up to or beyond 36 months under the conditions studied. These are class-specific figures, not one countdown. Inside a large power transformer, the bottleneck becomes physical. Grain-oriented electrical steel is cut and stacked into a core. Continuously transposed copper conductor becomes windings, surrounded by insulation and connected to bushings, tap changers, tanks, and cooling systems, the component map identified by Commerce. In an illustrative engineering reading, these stages manage heat, electrical stress, leakage, or insulation conditions before the unit is dried, filled, assembled, and tested. The map is not a list of proven shortages. It shows why a qualified unit depends on multiple stages. Material economics limits scale. A commerce survey cited by DOE found grain-oriented electrical steel and continuously transposed conductor copper each represented about 25% of final large power transformer cost in 2020. DOE reported about 80% of U.S. GOES consumption was imported in 2019, with Japan and South Korea among the sources. It also identified one active domestic GOES supplier meeting roughly 12 to 20% of demand. Those are dated supply pictures, not proof that one country controls the chain. Material availability can enter the qualification schedule at the factory. The schedule is stage-gated, not simply serial. Steel, copper, insulation, bushings, and cooling hardware must be available when their stage begins. A late input may leave a crew or test bay waiting. DOE also identifies difficulty hiring welders, coil winding workers, and testing personnel, with few specialized training programs. The useful unit of analysis is a qualified system, not a factory shell.
In 2019, DOE recorded 137 large power transformers made domestically, 617 imported, and 4 exported. It also characterized domestic utilization at about 40% and derived a theoretical maximum of about 343 units per year. That 343 is nominal capacity implied by the calculation, not qualified machines ready to ship. The 617 imports are a separate count, not domestic slack. Product mix, materials, labor, tests, and specifications decide which slots become usable machines. Adding slots takes time. DOE estimates 1 to 3 years to build a new large transformer factory, while specialty winding machines and core tables can take 1 to 2 years to procure. The deep dive also identifies difficulty hiring welders, coil winding workers, and testing personnel, with few specialized training programs. The machine America needs depends on machines and people on a long schedule. Then comes the test bay. DOE says a large power transformer test can take about 1 week, and facilities often have only 1 or 2 test beds. A finished unit can wait for a bed. A failed test can require diagnosis, repair, and retesting. Assembly completion does not release capacity on demand. Qualification is a production bottleneck, not an administrative stamp. Passing the test still does not energize the machine. DOE describes a chain through special transport, site delivery, and installation. The last 5 to 10 miles can be especially difficult and costly. A transformer may need route surveys, rail or road coordination, bridge and clearance checks, port handling, and a timed move into a substation. The obstacle is whether the destination can accept an object designed for one precise electrical location. The completion date on a factory schedule is not the service date on a data center schedule. Design, pre-qualification, manufacturing, testing, transport, installation, and grid integration have to line up. A digital project can accelerate for months, then discover that its slowest dependency is the qualified system that makes power usable. The digital demand is real. DOE estimated U.S. data centers used 58 terawatt-hours in 2014 and 176 terawatt-hours in 2023, with 325 to 580 terawatt-hours modeled for 2028. It estimated their share at 4.4% of U.S. electricity in 2023 and 6.7 to 12% in 2028, attributing growth to AI, manufacturing, and electrification together. LBNL's June 2026 update gives a 649 terawatt-hour 2030 reference case, or 11.8%, with a 521 to 843 terawatt-hour uncertainty range. But electricity demand is not transformer output. LBNL models equipment shipments, device energy, cooling, facility types, and locations,
and says it does not directly address grid or on-site supply.
NERC projects 224 gigawatts of additional North American peak demand over 10 years and says AI and digital data centers account for most of it, but bases the forecast on utility commitments and interconnection information. Older lanes remain. DOE cites aging replacement, transmission expansion, renewable generation, and storage for large transformers. It reports 55% of distribution transformers are older than 33 years and names EV charging, manufacturing, failures, and new customers alongside data centers. EIA attributed expected 2025 and 2026 consumption growth primarily to semiconductor and battery factories and data centers. AI accelerates the collision. It did not create every demand lane. The April determinations equipment list is broad. It reaches from transformers and substations to conductors, high-voltage breakers, power control electronics, relays, capacitor banks, electrical core steel, raw materials, and manufacturing tools. The administration says limited domestic production, procurement time, foreign dependence, and capital limitations create a national defense concern. The determination waives the listed Section 303 requirements and directs the Energy Secretary to make purchases, commitments, and financial instruments supporting production capability or other DPA action. Those tools could change the investment signal. A purchase commitment could make a specialized line easier to finance. A financial instrument could reduce the risk of ordering equipment before a utility contract is visible. But the determination names no dollar amount, factory award, completed project, or delivered transformer. It is authority and diagnosis, not measured throughput. The government can direct capital tools. It cannot instantly train a crew, create a test bed, qualify a design, or move a finished unit through a constrained route. The industrial response is visible, but status matters. On June 29, 2026, Hitachi Energy said its $457 million South Boston large power transformer facility was under construction. GE Vernova completed its Prolec GE acquisition in February 2026, reporting 5 U.S. sites, and announced nearly $600 million in U.S. factory and facility investment over 2 years. These are company-reported construction, ownership, and investment facts, not delivered output. Other routes target waiting time. DOE reports more than 80,000 distribution transformer varieties, while a March 2026 webinar gives almost 40,000 configurations. The difference shows why standardization needs a defined scope. Securing GOES and managing broader copper demand could strengthen inputs, but those are goals, not delivered resilience. DOE's flexible and solid-state concepts remain R&D or prototype paths, not mass production. Grid design can change timing. FERC's June 2026 action considers staged connections through faster studies, co-location, behind-the-meter generation, and flexible loads while addressing cost shifting. That may speed a campus connection, but it cannot erase qualified equipment needs. DOE's 2021 to 2024 review warns that facilities under construction may not operate until 2026 to 2030, and says large power transformer lines were operating at roughly 40 to 50% of current production line capacity. Usable capacity arrives only when skills, inputs, tests, and customers align. Now the consequences can be stated without apocalypse. If committed data center growth outruns generation, transmission, and transformer delivery, chips may be ready first. If forecasts fall, equipment may be sized for delayed or absent load, raising stranded asset and cost allocation risks. NERC's 224 gigawatt figure is a 10-year North American peak demand forecast based on commitments and interconnection information, not a current order book. Separately, EPRI and EPOC describe a global, low-confidence 2030 scenario of 4 to 16 gigawatts for one frontier AI training run, without modeling detailed power supply bottlenecks. Return to the transformer moving through the landscape. It looked like a slow object blocking a fast future. Now it is the visible edge of a larger machine. Steel, copper, factories, workers, test bays, transport, utilities, finance, standards, and decisions about who pays. America does not win the AI race simply by buying more accelerators. It wins when the physical system turns them on reliably at the speed investment assumes. The slow machine is not outside the AI race. It is the industrial coordination that lets the race happen.